students, we are seeing modeling of transformers in distribution system, and in the last two lectures we have seen modeling of single phase transformers, and basically to see the modeling of three phase transformer we have seen various types of conversions as well as representations. So, before going to actual modeling of different types of transformers, those are actually Y-Y connected or delta-delta connected or delta-Y connected. Let us revise whatever representation we have seen once again. So, before going to actual modeling of these three phase distribution transformers, which are having various different types of connection, that is those are Y-Y connection or delta-Y connection or delta-delta connections. Before going to that, let us see the representation of different voltages and currents. So, in case of grounded Y connection, we are writing it as a line to neutral voltages, which will be represented by this one. Sometimes if it is grounded neutral, we can write VAG also. So, VAG represent A phase to ground voltage, and if in case of ungrounded neutral, so if this neutral is grounded, neutral terminal available, it is grounded, then I will say VAG, and if it is ungrounded, means if this grounding is not there, then I will say VAN, voltage with respect to neutral terminal. And as I told you, we are going to call these three voltages collectively as V line to neutral voltage. So, I will say VLN ABC. So, these are basically line to neutral voltages of ABC phases, and secondary side also it will be VLN small ABC, which represents secondary side line to neutral voltages. Then line currents will be represented like I ABC on primary side and I small ABC on secondary side. In case of delta-delta connection, we have seen that we are representing voltages using line to line voltages, that is VAB, VBC and VCA, and collectively we can call it as a V line to line VLL ABC. So, when I am saying VLL ABC, they will be line to line voltages of all the three phases. Again this will be IABC. However, delta current collectively I am calling IDABC. These are the delta current which are after line current go inside this one, there will be delta winding and these line currents will get distributed. So, there will be different line currents and delta currents will be different. So, collectively these three current, as I told you, we can call it as a IDABC. Similarly, on secondary side, these are the line to line voltages. So, this will be VLL small ABC, and these are line currents. So, it will be I small ABC, and these three delta currents, they are basically IDABC. This is related to representation, and basically we are interested in getting ABCD parameters to model these transformer. For various connections, we want to get ABCD parameters. So, we have calculated ABCD parameter for single phase connection 2 winding transformer, where ABCD parameters are just one number. However, since if you observe, these are actually three phase voltages, which are 3 voltages, this also 3 voltages, there are 3 currents on primary side and secondary side. So, because of that, your A parameters will be having 3 by 3 matrix, B parameter will be 3 by 3 matrix, similarly C 3 by 3 and D also 3 by 3. So, ABCD parameters will be basically 3 by 3 matrices we can get, which we are interested in. So, always on this side we want to bring line to neutral voltages, even though it is delta connection. For that case also we need to bring ABCD parameters in terms of line to neutral voltages, and secondary side also, or we can say the secondary side voltages also we want line to neutral voltages. So, on this side of the parameters and on this parameter source side quantities also we want to be line to neutral and current to be line to line. So, always remember this. One more thing we have seen many times during the calculation, we want to know the load side voltages in terms of source side voltages and load current. So, to get this load side voltages in terms of source side voltages and load side current. So, in that case we are writing this as capital AT parameter and capital BT parameter. So, we are interested in small at, small bt, small ct and dt, and then capital AT and capital BT. Let us see how we can get it for different connections. Before that, I will just revise the terminology. Turns ratio, we are going to see it is voltage on primary side, or generally in case of distribution it will be HV side. So, voltage on primary side divided by rated voltage on secondary side. So, for different configuration depending upon phase voltage, means voltage across the winding you have to see while calculating turns ratio. So, in case of delta transformer, voltage across transformer delta side winding will be line to line voltage. So, that is why we line to line rated voltage divided by, in case of star connection it will be line to neutral voltage which will be appearing across the winding. So, that is why it will be VLN, line to neutral. Then ZTBC we have seen it is a diagonal matrix of impedances of 3 phases. There is possibility that many times these impedances will be same. Then we have seen this AV transformation matrix, which is basically your turns ratio in all the 3 phases. Generally this turns ratio will be same, and then AI will be inverse of your turns ratio, that is 1 upon NT, 1 upon NT, 1 upon NT and all others. So, in this case also it will be AI also will be diagonal matrix, only thing is it will be 1 upon NT, and since the turns ratio of all the 3 phases will be generally equal during operation also, these 3 terms will be equal. Then we have seen various voltage transformations. So, for transforming line to neutral voltage to line voltage, we have got D matrix. Then to convert line to line voltages to line to neutral voltages, we have got this W matrix. And in case of current conversion, to convert delta phase currents to line currents, we have got this K matrix, and to convert line currents to delta phase currents, we have got this L matrix. However, there are 2 cases, because depending upon zero sequence current path is available or not, we need to use L or M alternately. So, whenever there is zero sequence current path is not available, we have to go for L transformation, and whenever zero sequence current path is available, we have to go for M matrix. Okay, let us start with our first and simplest connection, and many times you will find these connections in power system application, that is grounded Y by grounded Y connection. It is very simple. So, to show the connection so that you can easily understand, I am just drawing it here and then we will see the expression. So, this connection will be something like this, joining, say these are the 3 transformers here. Okay, then as I told you, we are linking this impedance on the secondary side. So, impedance of all the 3 transformers, I am just showing it secondary side, and since we are going to connect them in star both the windings. So, this is your A phase, this is your B phase and this is your C phase, secondary side small letters, and then we need to make this star point here. So, this is connected to star point, this is star point, and since we are using grounded Y connection, we need to ground it. Okay. Then representation of impedances will be like this. So, this is impedance in A phase, impedance in base B phase, impedance in C phase ZT C. So, I should say ZT. And then currents are basically current which are coming out of this transformer, which is this current is IA, this current is IB and this current is IC. So, small IA, small IB and small IC. Um Now, primary is also grounded Y connection. In that case, you are having these three terminals which are basically capital A, capital B and capital C, and we need to make star point by connecting these other three terminals together, and which will be basically grounded, and this terminal I am calling it G, and this is a small g. Basically both terminals are same. However, to represent primary side and secondary side, I am writing capital G and small g. However, they are actually same terminals. Then primary side current will be IA, this current will be IB, and this current will be IC. So, voltage across the winding, it will be VAG, because to represent grounded terminal instead of neutral, even though this is neutral point, to differentiate between ungrounded neutral and grounded neutral. So, if it is grounded neutral, I am using, instead of N, I am using G. So, it will be VAG, it will be VBG and VCG, capital letters. Voltage across the terminals VTA, VTB and VTC, and the voltage of this terminal will be V small ag with respect to ground. Voltage of this terminal will be VBG with respect to ground, and this will be VCG with respect to ground. So, this is how we can actually draw the different connections. Now, if you see voltages at the terminals, that is VTA, VTB and VTC, these voltages will be nothing but, so VTA will be equal to V of AG plus your ZTA into IA, and then VTB will be equal to VBG voltage plus ZTB into your IB, and VTC will be equal to VCG plus ZTB into IC. And as I told you, we can collectively write these three terms together. So, this will be nothing but VTABC, which represent all these three voltages, which will be equal to, these are basically, as I told you, line to ground voltages. So, we can use term VLG, because in this case also neutral is grounded, VLG small abc. So, these three voltages will be represented by this, plus your impedance matrix ZTABC, which, as I told you, it will be diagonal matrix ZTA, ZTB, ZTC, and non-diagonal entries will be equal to 0. So, ZTABC will be having structure like this, and then multiplied by your IABC, all the three currents. One more thing we know, these voltages VAG, VBG and VCG capital, they will be just related by turns ratio with respect to your terminal voltages on secondary side. So, I can easily write, so VTA, or it is opposite way, VAG, VBG and VCG capital, they will be just equal to turns ratio multiplied by your terminal voltages, those are basically VTA, VTB and VTC. So, in this case, we can again collectively write these terms as VLG capital ABC, which are basically these three voltages, will be equal to this matrix we have given name as AV. I explained this AV matrix, we already defined it, and this is nothing but your VT ABC. Okay. And as I told you, we for writing this or getting this model in terms of ABCD parameter, we need voltages in terms of line to neutral voltages, and currents are basically line to line currents, line currents. Okay. So, what we can do, we can take this VT ABC and put into this expression. So, I am having this expression, I will explain you. So, basically we have got this VT ABC, which I explained is basically line to ground voltages of these terminals, that is VAG, VBG and VCG, which is basically in this particular matrix, and all the 3 terminal voltages, those are VTA, VTB and VTC, which are in this VTABC matrix. This is impedance matrix and line current matrix we have derived in last slide. Similarly, I explained you the terminal voltages, and on primary side and terminal voltage secondary side, they will be just related by NT, means terminal voltages means I am talking about winding voltages, they will be just related by turns ratio, and turns ratio matrix we defined as AV matrix. And then what we can do, this VTABC I can just put into this expression. So, after putting I will get this expression. So, here where VTABC I am taking it from here. So, VTABC will be replaced by this here, and then AV matrix I am taking inside the bracket. So, this term will get multiplied by AV, and this term will get multiplied by AV multiplied your ZT ABC. So, if you observe this equation, we have got this equation in required format, that is voltages are actually line to neutral or line to ground voltages. Ground we are, as I told you, we are using it alternatively to the neutral. So, these are basically line to ground voltages or line to neutral voltages, and this ABC line ABC, this IABC is nothing but your line currents. So, definitely this will become your A parameter AT, and AT I am writing because transformer. So, A parameter of transformer I am writing AT. If it is for regulator I can say AR. So, AT, and then it is this parameter is your BT. So, let us see what we are getting. So, as I told you, we are getting this as a parameter AT, and this is B parameter BT, and AV. So, A parameter just AV, and AV we have defined, okay, here there is mistake, it should be 0 here. So, AV matrix is just diagonal matrix of your turns ratio, and BT we are getting AV multiplied by ZT ABC. So, in this case also this is diagonal matrix of impedances, and this is also diagonal matrix of turns ratio. So, in that case your B matrix will be just diagonal matrix of turns ratio multiplied by your impedances of this one, and many times as I told you impedances of all the 3 transformers are there same, then in that case the entries will come out of the matrix, and then there will be 1 1 1 here, and then I can take NT into ZT common out if the impedances are same, and in that case it will be unity matrix. So, these are AT and BT parameter. Let us see how we can get C parameter and D parameter. C parameter and D parameter we can get it from current equations. We have seen current transformation equation, that is the current which is flowing in primary side and current which is flowing in secondary side. In this case current which is flowing in the primary side is IA, and current which is flowing in the secondary side is opposite direction, it is small IA. Okay, so, winding current also in this case, this winding current is IA and this current winding is small IA, and they will be related by your turns ratio, means your this IA will be equal to 1 upon NT into small IA. Similarly, IB will be just 1 upon NT into small IB, and then IC will be equal to 1 upon NT into small IC. And in that case you are right, this as I told you, this AI matrix is nothing but diagonal matrix of 1 upon NT terms, which I am writing it here. Now, if you observe it here, if you compare this with our required ABCD parameter matrix, where we want actually your primary side current in some terms of secondary side voltage and secondary side currents. If you compare this equation 1 and 2, you can see that there is no voltage related term, means your CT matrix will be 0, and the current related term is AI. So, in that case your DT matrix will be AI. So, DT will become equal to AI and CT will be 0. So, CT will be 3 by 3 matrix of zeros, and DT will be 1, as I told you. AI matrix we have seen 1 upon NT, 1 upon NT, 1 upon NT. This is basically coming from your current transformation. So, we have got small t, small d matrix also for this simple configuration, which is grounded Y by grounded Y connection. Then capital B and capital A and capital B. In that case, as I told you, we need to write your secondary side voltages in terms of primary side voltages and secondary side current. So, we have got this equation here, and we want to actually write this equation secondary side voltage in terms of primary side voltage and secondary current. So, we can take this on left hand side. So, in that case, if you take this on right hand side and then if you multiply everywhere by AV inverse, in this case it will become VLG ABC, which is secondary side voltage in terms of primary side voltage and secondary current. So, we have got in required format. So, this will be nothing but your capital AT matrix and capital BT matrix. So, AV inverse, AV matrix we have seen, it is just NT, NT, NT diagonal elements, and then when you are taking inverse of it, it will be just 1 upon NT, 1 upon NT, 1 upon NT in diagonal elements. And BT matrix is matrix of impedances. So, 3 impedances in the diagonal term. So, we have got BT matrix. Let us go for another configuration, that is delta grounded Y connection. This is also a widely used configuration where primary side is delta connected and secondary side is grounded Y connection. Okay. So, we will try to draw it here. So, I will first draw 3 transformers. This is your secondary side, okay, and then as I told you, we are referring your impedances on secondary side. So, all the impedances are connected secondary side, and this terminal we have seen small a, b and c, and since secondary side is grounded Y connections, I can take this terminal together and make your neutral point, and we can ground it, and I am calling it as point G. And primary side it is connected in delta. So, in that case we can connect all these windings into delta fashion. So, they are now connected in delta fashion, and then we can take each terminal out. This is your capital A terminal, B terminal and C terminal, and the currents are, this is IA, IB and your IC. Now, this voltage will be, voltage across this winding will be VAB, this will be VBC and this will be VCA. Similarly, these currents which are flowing through this winding this winding will be IAB, this will be IBC and ICA. So, these are delta, basically delta current. These terminal voltages on secondary side, it will be VTA because they are grounded Y connection. So, this is VTB and VTC. These impedances are ZTA, ZTB and ZTC. This current is small I, small b, and then this is small c. So, in this case also, first equation which we will write, the terms which are related to secondary terminal voltage, that is in terms of VTA. So now in this case I am directly writing it. So VTABC, which are basically terminal voltages, we can easily write them. They will be equal to VLG. Now since this is actually ground connection, ABC plus your impedance ZTABC, impedance matrix, which is again diagonal matrix of 3 impedance entries, and then line currents, which are basically small IABC. So this includes all the 3 currents, those are IA, IB and IC on secondary side. This include all the terminal voltages, those are VTA, VTB, VTC as a column. This represent all the voltages on secondary side, those are basically VAG, VBG and VCG with respect to ground, basically neutral connection. Since neutral is grounded, I am using G term here. And then one more equation I can write, which relates your primary voltages, primary winding voltages with respect to secondary winding voltages. So VTA and VAB, they will be just related by your turns ratio. Means I can easily write VLL, because now these voltages are line to line voltages, VLL ABC, which basically VAB, VBC and VCA on primary side, they will be equal to the transformation ratio matrix, which you have seen, it is matrix AV multiplied by your VTABC. So VTABC multiplied by your transformation ratio matrix will give me line to line voltages. Okay. Then what you can do, exactly similar way what we did in case of earlier case, whatever this VTAB we can put it here. So in that case your equations will be VLLABC, which will be equal to your matrix AV into VLG small abc plus AV into JTABC into IABC. Now if you observe this equation here, as I told you, whenever we are writing or whenever we want to get ABCD parameters, always there should be line to neutral voltages and line currents. So if you observe this equation here, this term, this is actually line to neutral voltage, so we don't have to worry. This term also line to line currents, so we don't have to worry. However, on this side we are getting line to line voltages, which need to be converted to line to neutral voltages. So we have seen that conversion matrix for converting this into line to neutral voltages, we need to multiply this equation by equation W, matrix W, which is basically conversion matrix, which will convert your line to line voltages into line to neutral voltages. So everywhere I am just multiplying this equation by W, so if you multiply it by W multiplied by V line to line will be basically will to become V line to neutral into ABC here, and it will be actually W as it is, WAV into VLG small abc plus your W into AV into ZTABC into IABC. So we have got in required format. So these voltages are line to neutral voltages and currents are actually line currents. So definitely this must be your parameter AT and this will be your parameter BT. So let us see what are these parameters are. So we have seen these equations. So we have got AT which is equal to W multiplied by AV. W matrix we know, which is this one, and AV matrix is just transformation matrix, which is NT, which is diagonal matrix. So, we can easily write NT, these are diagonal, which will get multiplied to each end of the entry. Basically, it will come out of the matrix. So, it will be NT by 3 and to this particular matrix. So, your AT parameter will be given like this, and we have seen that your BT parameter is W multiplied by AV multiplied by your ZT ABC. So, in this case also this ZT ABC diagonal matrix, in that case this will get multiplied to each of the entry of this matrix. So, if you multiply these two matrices, basically since it is diagonal, each entry will get multiplied with respect to diagonal entry of this one. So, in that case the matrix which is after multiplying, you will get this matrix here. And as I told you, if impedances are same, generally they are same, in that case impedances will also come out. So, in that case your matrix will be NT into ZT if they are equal, divided by 3, and this is 2 1 0 0 2 1 1 0 2. So, this will be your BT parameter. So, you got AT and BT for delta and grounded Y connection. Let us see how we can get currents. So, in this case first we will take currents which are winding currents. So, as we know that winding currents are related by turns ratio. So, on this side winding current is IA. So, the current which is flowing through the secondary winding is IA and IB and IC. However, on primary side the currents are IAB, IBC and ICA, which are basically delta currents. So, collectively I can write these delta currents which are basically IAB, IBC and ICA, and we have seen that whenever there are delta current I am writing this D term here. So, ID, ABC represent these delta currents on primary side. So, capital letters are here and they are related to the secondary side currents which are basically IA, IB and IC. So, this basically this term represent your currents IA, IB and IC, and they are just related by your turns ratio transformation, which is basically AI matrix, which is 1 upon NT, 1 upon NT, 1 upon NT in the diagonal terms, and non-diagonal terms are 0. So, we are getting this matrix. Now, since there are delta current, because as I told you for ABCD parameters we need line currents. So, we need to convert these delta currents into line currents. So, basically these are line currents, we do not have to worry, these delta current need to be converted. So, these we can get we know this equation which basically converts delta currents to the line currents of IABC. So, we can use this equation here. So, your IABC, and instead of this IDABC I can just put this equation here. So, it will become actually your K multiplied by AI multiplied IABC. Now, we can compare with this your standard equation of ABCD parameters. The standard equation is this one, say 2, and this is which equation which you are getting 1, and if you compare this 1 and 2, you can see that there is no terms which is related to VLN. That is why CT matrix will be equal to 0, 0, 0 of 3 by 3 size, and your DT matrix basically is nothing but this K multiplied by your AI. AI is basically diagonal 1 upon NT terms. So, you can easily see that your C matrix is basically matrix of 0 0 zeros, and your DT matrix is K multiplied by AI. So, K matrix we know, which is given by this, and AI matrix which is basically given by this. And in this case also NT, actually these are diagonal entries which will get multiplied by corresponding entries into the matrix, and since they are diagonal, it will come common. So, 1 upon NT, and this will remain same. So, this is nothing but your matrix DT here for delta to grounded Y connection. So, I got all ABCD parameters. Let us see capital A and capital B parameters. So, we want to make this load side voltages in terms of source side voltages, and so we will just write that way by taking this on left hand side and this on right hand side. So, if you do that, it will basically I will get this equation here. So, this term will be equal to this term minus basically this term. So, after doing that I will get this term here. Then what we need to actually remove this W and AV. To remove this W and AV, what we need to do is we have to multiply whole equation by your AV inverse multiplied by W inverse. So, if you multiply this whole equation by AV inverse multiplied by W inverse, this term will get cancelled out because AV we are multiplying by AV inverse and W inverse. So, on this side only VL will remain. This term will get multiplied by this AV inverse by W inverse, which I have written it here, and in this term also if you multiply this term by AV inverse and W inverse, only ZT ABC will remain. So, here in this term only ZT ABC will remain. Now, as I told you, whenever you are getting W inverse, you need to use matrix D, or whenever you are getting D inverse, you need to use matrix W. So, here we are getting this W inverse here. So, this should be replaced by matrix D, and then we can compare this with our standard equation of capital A and capital B parameter, which basically gives secondary side voltages in terms of primary side voltages and load currents. So, you can easily compare. So, this will become your parameter AT and this will become your parameter BT, and by knowing AV inverse and D, we can easily get your parameter capital AT, which is basically AV inverse multiplied by D, and AV inverse is nothing but, because AV is just diagonal entries of NT, NT, NT. So, it will be 1 upon NT, 1 upon NT, 1 upon NT, which is basically AV inverse, and this is your D matrix. So, since these are the diagonal entries, it will be just 1 upon NT, and this is your D matrix here. So, in summary of today's lecture, we are actually seeing various models of distribution transformers. To start with, we have revised all the transformation matrices which basically convert voltage and current transformations, those we have revised, and then we have seen two types of transformer connections which are basically grounded Y to grounded Y connection and delta to grounded Y connection, and in both these cases we derived ABCD parameters and capital A and capital B parameters, which basically used while modeling the transformer. Thank you.